Good morning, all of you, and welcome to the today's session on stress-strain relations. So, last class we studied about the relation between the strain and displacement. So, from the strain and displacement, we can find the strain values if you know the displacements. So, in this session, if you know the strain values, how we can find the stresses. So, to find the stresses, we have to build a relation between the stress and strain relations. So, in this one, we have the two parts. One is a three-dimensional body and second one is a two-dimensional body. Today we discuss the stress-strain relations for the three-dimensional body. So, from the Hooke's law, we know that for three-dimensional body, the different strains acting in x direction, y direction and z direction. Suppose first we can take that the strain acting in the x direction, epsilon x equal to sigma x by e minus mu into sigma y by e minus mu into sigma z by e. So, in this one, sigma y by e is the longitudinal strain and another two are the lateral strain. So, here sigma mu minus mu into sigma y by e is a lateral strain due to the load is acting in the y direction but the strain is acting in the x direction. Similarly, minus mu into sigma z by e is a lateral strain. It is also due to the load in the z direction but it will act in the x direction. So, totally the total strain in x direction for three-dimensional body is sigma x by e minus mu into sigma y by e minus mu into sigma z by e. In this one, the one is a longitudinal strain, another two terms are the lateral strain. Similarly, we have the strain in the y direction, epsilon y equal to. So, in this epsilon y, one is a longitudinal strain, that is a sigma y by e is a longitudinal strain, the another two are the lateral strain. So, for example, minus mu into sigma x by e is a lateral strain. This is due to the load acting in the y direction but the strain will be act in the x direction. And similarly, sigma y by e is a longitudinal direction. Here the load is acting y direction as well as the strain also acting in the y direction. And the other one is a lateral strain. So, this is a lateral strain. So, minus mu into sigma z by e. This is due to the load is acting in the z direction but the strain will be act in the y direction due to the z direction load. So, this equation also epsilon y also have the two lateral strain, one longitudinal strain. Longitudinal strain is sigma y by e. Similarly, epsilon z. So, this is a strain acting in the z direction. It is also contains the two lateral strains, one longitudinal strain. So, it is first one is minus mu into sigma x by e. It is a lateral strain and this lateral strain is due to the load is acting in x direction but the strain will be act in the z direction. And next one is minus mu into sigma y by e, also lateral strain but this is due to the load is acting in the y direction but the strain will act in the z direction. The last one is a longitudinal strain, that is a sigma z by e. So, this is a equation number 3. Apart from this one, we know that shear more or less G equal to tau by epsilon ig. Here tau is a shear stress and epsilon ig is a shear strain. G is a modulus of rigidity. So, from this one, the strain epsilon xy equal to, we can take that epsilon xy equal to tau xy by the G is a modulus of rigidity. So, here you have to observe one thing. If we are taking the strain xy means the stress also we have to take xy. So, epsilon xy equal to tau xy. Apart from this one, we know that the relation between the Young's modulus and the G. So, here epsilon xz equal to tau xz similarly and epsilon yz equal to tau yz by G. And in this one, we have to replace G with the Young's modulus. Why? Because experimentally, we can find the Young's modulus of all the materials and if we require the G means with the comparison of with the relation between the G and E, we have to find the G. So, all data books contains the Young's modulus of the materials and because of that one, we have to ensure that all equations are with in terms of young smallest. So we know that the relation between the G and E, that means E is a young smallest, G is a smallest of rigidity. So E equal to 2G into 1 plus mu. So this we can get from the basics of mechanics of solids. So from this one, G equal to, from this equation we require the G. So G equal to E by 2 into 1 plus mu. So this is the equation number A. Now to convert the equation number 4, 5, 6 in terms of the E, otherwise to eliminate the G in equation number 4, 5, 6, we have to substitute the equation number A in equation number 4, 5, 6. So if you simply substitute the G equal to E into 2 in E by 2 into 1 plus mu in equation number 4, 5, 6, then we will get the epsilon xy equal to, the shear strain xy equal to 2 into 1 plus mu by E and into tau xy, and similarly epsilon xz equal to 2 into 1 plus mu by E into tau xz, and next last one is the shear strain epsilon yz equal to 2 into 1 plus mu by E into tau xy. So the total in 3-dimensional body, the total we have the 6 strains, the 3 are the normal strains and 3 are the shear strain. What is the normal strain, what is the shear strain, all we discussed in the first class. Now you write the equation number 4, 5, 6, 7, 8, 9 in the matrix form, then we will get the relation between the strain and stress. So to find what is called the relation between the strain and stress, write the equation number 4, 5, 6 in the matrix form. So for that one, suppose say we have what is called epsilon x. Epsilon x equal to sigma x by E minus mu, sigma y by E minus mu, sigma z by E. So here 1 by E you take the all the equation, 1 by E is a common. If you take the 1 by E, then you take the what is called empty matrix. So always you have to follow this one to convert the equations into the matrix form. So first you have to take the right side one, the right side vector equal to a common factor 1 by E, any common factor, then you keep the empty matrix. So this is a coefficient matrix or constant matrix into the variable matrix, that is a sigma x, sigma y, sigma z, tau xy, tau xz, tau yz. Now you have to go equation by equation. Suppose I taken the first equation, we have to convert this equation number 1, 2, 3 and 4, 5, 6 into the matrix form. So for example, I will take the only one, that is epsilon x is the equation number 1. So sigma x by E minus mu into sigma y by E minus mu into sigma z by E. In this one, 1 by E I taken the common. So suppose you have to a vector, you have to come row by row. Sigma, first one is a sigma x. In the equation number 1, sigma x is here. So the remaining one is a 1 by E. 1 by E I taken the common. So the coefficient is only 1. So here 1. That means if you can multiply this one minus 1 by E into sigma x, you multiply this row into column, then you will get this one. So 1 by E into sigma x. Similarly, the sigma y. What is the second one? Second one is a sigma y. Here second, other than sigma y, we have the minus mu by E. 1 by E taken the common, the remaining one is a minus mu. So here minus mu. And then minus mu into sigma z by E. So the third one is a sigma z. So sigma z, the remaining one is a minus mu by E. That means for sigma z, the coefficient is a minus mu by E. This minus mu by E, already 1 by E I taken the common. So the remaining one is a what is called minus mu. And after that you have what is called tau xy. So there is no tau xy in the equation number 1. So the coefficient of the tau xy is a 0. And similarly tau xz. So there is no tau xz in equation number 1. Then the coefficient of tau xz also 0. And then is tau yz. In equation number 1, there is no coefficient of tau yz. So the coefficient of tau yz also 0. So like that I completed the equation number 1. Similarly you have to complete the equation number 2, 3 as well as what is called 4, 5, 6. That means the equation of epsilon x, epsilon y, epsilon z and equation of epsilon xy, epsilon xz and epsilon yz. So then So always you have to go equation by equation. Suppose you take the epsilon y. So epsilon y is what? Minus mu into sigma x by e. The coefficient is a minus mu by e. So 1 by e I taken the common. So the remaining one is a minus mu. Then equation number 2, second term is a longitudinal strain, that is a sigma y by e. So 1 by e I taken the common, remaining one is a 1. Similarly, minus mu into sigma z by e. So the minus mu by e is a coefficient, 1 by e is common. So minus mu is a only minus mu is a coefficient. So that means, say, suppose equation number 1, you multiply the row and column, you will get the equation number 1 by e into 1 into sigma x is a sigma x by e, 1 by e into minus mu into sigma y, that is minus mu into sigma y by e, then 1 by e into minus mu into sigma z, so minus mu into sigma z by e, the others is 0. So you get the equation number 2. Similarly, if we can multiply the row 2, second row and this one, you will get this equation number 2. Similarly, this is for third equation, you will get minus mu 1 0 0 0. That means if multiply the third row and column, you will get what is called third equation. And then you jump to the fourth equation. So 0 0, 2 into 1 plus mu 0 0. So you know that epsilon xy equal to, so already we have the epsilon xy, that equal to 2 into 1 plus mu by e into tau xy. Same equation taken as a equation number 4. So in this equation, suppose in this equation there is no sigma x. If there is no sigma x, means the coefficient of sigma x equal to 0. The next one is sigma y. There is no sigma y here. The coefficient of sigma y equal to 0. Then sigma z. There is no sigma z in equation. So the coefficient of sigma z is 0. Next one is we have the tau xy is there. So here we have the tau xy. The coefficient of tau xy is 2 into 1 plus mu by e. So you take the tau xy. The 1 by e is a common. The remaining one is a 2 into 1 plus mu. So you are taking the 2 into 1 plus mu. And similarly, tau xz is not there in this equation. So the coefficient is 0. And tau yz also is not there. So tau yz also 0. And similarly, you have to apply for the another 5, 6 equation. Here you have the 0, 0, 0. You have the equation have the tau xz have the only 2 plus 2 into 1 plus mu. And similarly, the last equation, all are zeros. Why? Because sigma x, sigma y, sigma z, tau xy, tau xz have the 0 coefficient. Only we have the tau yz. So 2 yz have the coefficient of the 2 into 1 plus mu by e. So 1 by e taken the common. So remaining one is a 2 into 1 plus mu. So this equation will give the relation between the strain vector and the relation between the stress vector. But we required not a strain, we require the stress. We know the strain. So from this strain, we need to calculate the stress vector. So this we require the stress vector. So this stress vector we required. So to get the stress vector, so the stress vector equal to inverse of this matrix. Suppose say this equal to, for simplicity I am taking the strain vector equal to epsilon, and this constant matrix 6 by 6 matrix I am taking as a C, and into this matrix is a stress vector sigma. So epsilon equal to C into sigma. Here epsilon is this 6 by 1 matrix, 6 rows and 1 column, and here C means 6 by 6 matrix and sigma means 6 by 1 matrix. So here I required what is called sigma. Whenever I required sigma from the basics of the properties of the matrices, so sigma equal to C inverse into epsilon. So sigma equal to C inverse into epsilon. So here stress equal to C inverse into epsilon. So here the derivation of C inverse is not required. So directly we can take the C inverse. So C inverse equal to sigma. This C inverse we can take as a D into epsilon. D equal to D. Otherwise say here D equal to C inverse. And this D we can call as a material properties matrix. This D we can call as a material properties matrix. So finally, the stress vector sigma x, sigma y, sigma z and tau xy, tau xz, tau yz equal to C inverse. So C inverse into the strain vector, that is epsilon x, epsilon y, epsilon z, epsilon xy, epsilon xz and epsilon yz. So the D matrix equal to, that means C inverse equal to E by 1 plus mu into 1 minus 2 mu into this matrix. In above equation, the 6 by 6 matrix. So here sigma equal to D into epsilon. So here above equation, the 6 by 6 matrix is a what is called D matrix. So a D is a material properties matrix. If you observe the 6 by 6 matrix, it depends only on the material properties, that is E and mu. E is a Young's modulus, mu is a Poisson's ratio. So the D matrix depends upon the only properties of the material, that too Young's modulus and Poisson's ratio, and because of that one, the D matrix is also called as a material properties matrix. The D matrix is, we can call as material properties matrix. Why? Because it depends only on the properties of the material. And in this above equation, the 6 by 6 matrix is a material properties matrix. So this is about the relation between the stress and strain for 3-dimensional body. Thank you. Thank you everyone.